Hello, welcome students. I am Rekha Thorat, Associate Professor. Today we will discuss nor on the normalizer of an element. Let us consider first the definition of normalizer or centralizer of an element. Let G be a group and A belongs to G be any element. Then the subset NA equal to set of all x belongs to G such that XA equal to AX bracket complete is called normalizer or centralizer of A in G. That means here G is any group, A belongs to G, NA is subset of G such that NA equal to set of all x belongs to G satisfying the property XA equal to X. Then the set NA is known as normalizer or centralizer of A in G. Now consider one theorem. The center ZG of a group G is a normal subgroup of a normalizer of an element. That means we have to prove that the center ZG of a group G is a normal subgroup of a normalizer of an element. Let us consider the proof of this theorem. Here we assume that ZG equal to set of all x belongs to G such that XG equal to Gx. For all G belongs to G, bracket complete, be the center of the group G. Here we denote notation ZG instead of NA. Let NA equal to set of all x belongs to G such that XA equal to AX be the normalizer of an element A in G. We have to prove that ZG is a normal subgroup of an A. Clearly both ZG and NA are subgroups of group G. Let X belongs to ZG, then X belongs to ZG implies XG equal to Gx for all G belongs to G, and this implies XA equal to AX for all A belongs to G. Here for element G, here for element A. This implies X belongs to NA. Here NA means set of all X belongs to G such that XA equal to X. So that here X belongs to NA. X belongs to ZG implies X belongs to NA. That is ZG is contained in NA. Therefore, ZG is a subgroup of NA. But since ZG is normal subgroup of a group G by the theorem 10, and hence ZG is a normal subgroup of NA by theorem 10. Here ZG is normal subgroup of group G, and by theorem 10 ZG is normal subgroup of NA. Now we consider the factor group or quotient group. Let us consider first one theorem on this part. Statement of this theorem is the set G by H equal to set of all HA such that A belongs to G bracket complete of all cosets of a normal subgroup H of a group G is a group under the binary operation defined by HA into HB equal to H of AB for all HA comma HB belongs to G by H. Let us consider the proof of this theorem. Let H be a normal subgroup of a group G. Since H is normal subgroup of a group G, therefore each right coset of H in G will be equal to the corresponding left coset of H in G by theorem. Hence, there is no any distinction between right and left cosets, and we shall call them as simply cosets. Let G by H equal to set of all HA such that A belongs to G. Bracket complete. To prove that G by H is a group under binary operation defined by HA dot HB equal to H of AB for all HA comma HB belongs to G by H, let HA comma HB comma HC belongs to G by H. Here we have to prove that G by H is a group under binary operation defined by HA dot HB equal to H of AB. And properties of proof we have to prove here for this G by H. First property is closure property. We have HA dot HB equal to H into bracket AH bracket complete into B equal to H into bracket HA bracket complete into B equal to H into H into AB equal to H into AB, since H into H is H. Since AB belongs to G, therefore H of AB is also a coset of H in G. So H of AB belongs to G by H. Thus, if HA and HB belongs to G by H, then H of AB also belongs to G by H. Here we assume that HA, HB, HC belongs to G by H. And in closure property, we prove that if HA dot HB equal to H of AB and H of AB belongs to G by H. Thus, G by H is closed with respect to multiplication of cosets. Now we consider second property, which is known as associativity. Let A comma B comma C belongs to G, then HA comma HB comma HC belongs to G by H. We have HA into HB into HC equal to HA into bracket HBC bracket complete equal to HA into bracket BC equal to HA into bracket AB bracket complete into C, and this is equal to in bracket HAB bracket complete into HC equal to in bracket HA dot HB dot HA dot HB bracket complete into HC. That means associative property is satisfied by these cosets. Thus, multiplication of cosets is associative in G by H. That means associative property is satisfied here in G by H. Now we consider next property, that is existence of identity element. We have H equal to HE identity element. HE is identity element. H can be written as HE belongs to G by H. Also, if HA is any element of G by H, then H into HA can be written as HE into HE. It is equal to H of EA equal to H of A, since EA equal to A. And similarly, HA into H equal to HA into HE equal to H of AE. It is equal to also H of A, since A equal to A. Thus, the coset HE equal to H is identity element in G by H. Now we consider next property, that is, thus we consider here H equal to H is identity element in G by H. Now we consider last property, that is existence of inverse. Let HA belongs to G by H. Then HA inverse belongs to G by H. We have HA into HA inverse equal to HAA inverse equal to HE equal to H, and HA inverse into HA equal to H of A inverse into A equal to HE equal to H. This shows that the coset HA inverse is the inverse of HA, that is HA inverse equal to H into A inverse. Thus, the property of existence of invert is satisfied, and all the four properties of group are satisfied by G by H. First property is closure property, second property is associativity, third is existence of identity, and fourth is existence of inverse. All the properties of group are satisfied by G by H. Hence G by H is a a group with respect to multiplication of cosets. Now we consider this definition of this quotient group or factor group. If H is normal subgroup of group G, then the set G by H of all cosets of H in G forms a group under the multiplication of cosets. This group is called the factor group or the quotient group of G by H. That means here G is a group, H is normal subgroup of group G, then the set G by H of all cosets of H and G forms a group under multiplication of cosets, and this group is known as factor group or quotient group of group G by H. Here one remark is there. The identity element of the quotient group G by H is H. These definitions, remark and statement of these theorems are considered for objective questions. Now we consider one example. Let Z plus be the group of integers, and let H equal to set of all mx such that x belongs to Z, bracket complete, be a subgroup of Z, where m is a fixed positive integer. Write the elements of the quotient group Z by H. Here in the solution, we consider that since Z plus is an abelian group, therefore H is normal in Z. The elements of Z by H are the cosets of H in Z, namely H plus 0 equal to H equal to set dash 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 comma minus 3m comma minus 2m comma minus m comma 0 comma m comma 2m comma 3m comma dash dash, bracket complete, and the set H plus 1 equal to, by adding 1 to this set H, that means set h plus 1 equal to set dash 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 comma minus 3m plus 1 comma minus 2m plus 1 comma minus m plus 1 comma 0 plus 1 that is 1 comma 2m plus 1 m plus 1 comma 2m plus 1 comma 3m plus 1 comma dash 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 bracket complete. And similarly we consider h plus 2, that is h plus 2 equal to set dash 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 comma minus 3m plus 2 comma minus 2m plus 2 comma minus m plus 2 comma 2 comma m plus 2 comma 2m plus 2 comma 3m plus 2 comma dash 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 bracket complete. That is by adding 2 to set h. Similarly, h plus 3 is the set adding 3 to set h, which is equal to set dash 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 comma minus 3m plus 3 comma minus 2m plus 3 comma minus m plus 3 comma 3 comma m plus 3 comma 2m plus 3 comma 3m plus 3 comma dash 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 bracket complete. And we continue the same process. And h finally h plus of m minus z equal to set dash 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 comma minus m minus 2 comma minus 2 comma m minus 2 comma 2m minus 2 comma 3 minus 2 comma dash dash bracket complete. And h plus in bracket m minus 1 equal to set dash 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 comma minus m minus 1 comma minus 1 comma m minus 1 comma 2m minus 1 comma 3m minus 1 comma dash 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 bracket complete.